Um, Hi, welcome everybody. My name is Bilal Yunus, and I will be continuing this course on how to quality check the lab PVT report, like the data that's generally reported in the PVT report, including different experiments, compositions, for example. And Matthias Carlson, my friend, he actually started the course initially, and he went through the introduction, and he has also mentioned very clearly that this course is mainly focused on doing the different quality checks and explaining the different methods and how you use those methods to actually do the quality check of the different PVT data, different types of PVT data in the PVT report. And that's something we don't discuss in detail in other courses, for example, like advanced PVT course. So this course is only dedicated to give you an opportunity to learn the different methods and apply them using using the PVT reports that we will be using in this course. We have a gas condensate PVT report and an oil PVT report, and both reports combine. Both reports kind of give you um, mm, like all the different experiments that are generally available in any PVT report. So you will have the opportunity to apply those methods on most widely available PVT experiments. He also, my friend, he also introduced you to the different types of QC that we will go through in this course. So one is this field-wide trend plots, and Matthias, he actually went through in detail what are the different plots that you can make. And here the basic idea is that if you have multiple samples, if you have data from multiple samples in a given field, you try to correlate them and you try to plot them such that the properties are generally correlated, and you see where which samples are outlier, and then you try to check whether it's due to bad measurement in the lab, or whether, and there you make a decision whether you should include that data in US model development, for example, or not. So Matthias Carlson, he has already went through these worldwide trend plots. What I will be focusing on this course is to go through the rest of the QC methods, so comparison with correlation, material balance checks, and compositional checks, and you can group them into one category, which is sample specific PVT data QC, meaning that if you have PVT data on one particular sample and you want to QC the data in detail reported for that particular sample, how would you go about doing it? So we will see what are the methods there and how you can use those methods. So first we will discuss this comparison with correlations, this method here. So there we will just jump to, yeah. So if you just come to this topic here. So here in this category, there are mainly two methods that we will be discussing. One is the QC of the gas Z factors, and the other one is the equilibrium check of separator samples. And as the name implies that this is like comparison with correlation, so we will be using some kind of correlation um, to see whether the reported data is of good quality or bad quality. So when it comes to gas Z factors, we will be using this standard card Z factor chart, and there will be certain correlations that we'll be using to come up with the properties needed to use the standing card Z factor. And so the gas Z factors, we know that they are reported, for example, in CVD and DLE experiments for all types of fluids. For example, if you have a gas condensate, or if you have a volatile oil or a black oil, if you have a CVD or DLE experiment, there is always the gas compositions reported in the experiment. And the gas Z factors in the CCE is only for gas condensates. Okay, and then yeah, so there we will be comparing the gas Z factor, the reported gas Z factors with the standing card Z factor chart values. The second method there, the second QC that we will be discussing is the equilibrium check of separator samples. There, the main idea is to see whether the collected samples and the samples that are analyzed in the PVT lab, they are actually in thermodynamic equilibrium. And the method we use is this Hoffman et al. Method. And there, the basic idea is that if you plot the log of Ki times pressure versus the Fi term, then it should be a straight line. And the slope and intercept of that straight line, we generally compare it with the standing correlation, which is for low pressure K values. So we will also go through in detail this method B. First, we can discuss this method A, which is for gas Z factors. So yeah, so as I've already mentioned, that the basic idea is that we will be comparing the lab reported gas Z factors with the standing cards Z factor chart values. And if you look at the standing card Z factor chart, maybe I can just show it to you in the monograph. It should be in chapter 3. So 3, go to, yeah, so here. Yeah, so this is this famous standing card Z factor chart, and here you can see that you have gas Z factors, and to get the gas Z factors, you need a pseudo reduced pressure, and you need a pseudo reduced temperature. For each line is based on a constant pseudo reduced temperature. So you need these two numbers to get the gas Z factor value from this chart. So this standing card Z factor, this is mainly function of, you have a pseudo reduced temperature and you have a pseudo reduced pressure. And what we looked at in this chapter, in the SPM monograph, this chart, one way of getting the standing card Z factor is that you go into the chart and pick the value manually. But this is again, this is not very user friendly, because if you want to like for example do the QC, you would like some automated method that helps you find the right value from that chart. So in that case, what this Yarborough method is very useful, because Yarborough, what they have done is that they fitted an equation of state model, like they fitted an equation to fit they use an equation to fit the entire standing Z factor as a function of this pseudo reduced temperature and pseudo reduced pressure. So I can just show it quickly here how that equation looks like. So that's this Yarborough equation. You have a Z factor as a function of this reduced pressure, and then this you have this dependency, and then you have this T here in the alpha term, that's the function of the pseudo reduced temperature. And here it's given like how you can solve it iteratively using the Newton-Raphson method. So here it's given the derivative is given, the function, this y function is also given here, and then the spreadsheet that we will be using for this calculation, this equation is already programmed, and it's a very accurate representation of the entire standing card z factor chart, and this helps us to automatically calculate based on the given TPR and PPR the accurate standing card z factor value. So yeah, so that's this Yarborough method that we'll be using, and what this TPR and PPR are actually, so the pseudo reduced temperature, that's actually just a ratio of the actual temperature at which this z factor is reported divided by the pseudo critical temperature, and same goes here, this is ratio of pressure versus the pseudo critical temperature. Okay, and one thing that I think it's important to mention is that this pseudo critical pressure and pseudo critical temperature, they are not the actual critical temperature and pressure of the gas mixture you are looking at. What does it mean? Like if you have the phase envelope for the given gas composition, like if you plot the pressure and temperature diagram of the given gas mixture for which you are looking, like the Z factor for which, the gas for which you are looking at these gas Z factor values. If you make the phase envelope of gas mixture, so you will have a critical point here somewhere, and this will have a critical temperature, and this will have a critical pressure. So what I was trying to say is that this critical pressure here is not the same as pseudo-critical pressure, and same goes for Tc is not equal to this Tpc, and that's the reason why these two properties, the pseudo-critical pressure and temperature, they are called pseudo-critical and not the actual critical temperature and pressure. That's just a short note on these properties here. Okay, so now what we will look at is the how you can actually calculate the TPC and PPC, because now we know that that's the required property to get the Z factor. So one method is case mixing rule, and it's a very simple method. If you know the total composition, so this method works when you know gas composition. So if you know the gas composition, then what this method says that the pseudo-critical temperature is just the sum product of Yi times Tci. So yeah, these are the mole fractions of each component in the gas phase, and these are the critical properties of each component. And same goes for PPC, which is sum product of Yi PPCi. Okay, and so you need to know the gas composition, and so you need to know, for example, what is the amount of nitrogen, for example, CO2, H2S, C1, C2, and so on until, for example, you have C6, and then you will have a C7 plus fraction. You need these amounts in mole percent, for example, or mole fraction, whatever. You need the component amounts for all the components. Now we know that the all these components like nitrogen, CO2, H2S until C6, these are kind of pure components, so you know the actual TC and PC for these components, and you can use it to calculate the TPC and PPC here. But what's missing there is that how do you get the TC and PC of this C7 plus fraction? Because the C7 plus fraction is unknown, you don't know what's the average property of that fraction, and it may vary from one gas to another gas composition. So there is this method, it's given by Matthews, and what this method says that the like TC and PC of C7 plus can be calculated if you know the molecular weight of C7 plus and the gravity of C7 plus. And the gas compositions that are reported in the PVT report, they generally have this information and the molecular weight and the gravity of the C7 plus fraction. So you can use those numbers to get the approximate value of the TC and PC of the C7 plus fraction. And once you have that, you can calculate the total the average TPC and the PPC of the entire mixture. The second method is this based on correlation, and their uh, uh, gas composition is not required. Okay, and so there you have there are different correlations. For example, you have what the correlation that we generally use and found found accurate actually is this certain correlation. And again, so here what this correlation do is that they give you TPC and PPC values as a function of gas gravity. So the only measurement that you need for the given gas composition is the measured gas gravity. You know that you can get the TPC and PPC values. So this correlation is given in the SPM phase behavior monograph in the chapter 3, and we'll be using this in this exercise. And so now what do we expect, like when we calculate the z factors from the standing correlation? What do we generally expect from the calculated z factor values, like how close they should be compared to the lab data? So the what we have found that this should generally be within plus minus 3%. So the lab data and the calculated data for the gas z factor should be within plus minus 3%. If it's in plus minus 3%, then it means that the data is of good quality. And this plus minus 3%, it includes both the measurement lab uncertainty. You can have some uncertainty there in the lab measurement, and also you know that we are using correlations. For example, here certain correlation. In this case, mixture rule, we have this Matthews correlation. So we are using certain correlations. So and correlations, we know they are not accurate. So there is some room, and this plus minus 3%, there is some room for this correlation accuracy. So, but overall, it should be generally within plus minus 3%, and that generally gives the idea whether it's a good quality data or a bad quality data. The other important aspect when doing the gas Z factor QC is the correction to the non-hydrocarbon contents, and this correction becomes very important if you have large quantities of non-hydrocarbons. So there the idea is that you actually need to correct, or you need to calculate a corrected TPC and PPC, knowing this epsilon, which is this is and the correction term. for non-hydrocarbons. This is a correction term, and again, these equations are given in the monograph how you calculate the epsilon value, and TPC star and PPC star, they are the pseudo-critical pressure and temperature of the entire gas mixture, including the non-hydrocarbon contents. And then once you have this TPC star and the epsilon value, you can get these corrected values of the TPC and PPC, which then you can use for calculating the gas Z factor. Now, how do you calculate this TPC star and PPC star values? So again, two ways of doing it. You have if you have the gas composition available, then it's straightforward, because then this TPC star is actually this TPC from case mixing rule, which is actually, as we mentioned before, yi times TCI, and this includes all the components, including non-hydrocarbon, this sum product. And same goes for the pressure. Now, if you don't have the gas composition available, the other alternative method is that if you should know the gas gravity, and then you should know at least the non-hydrocarbon contents and the composition of the non-hydrocarbon compounds in the gas mixture. So that's the at least you should know in terms of the gas composition. And there, it's the method is a bit complicated. There are three steps actually. So the first step is that you need to find out the gravity of the hydrocarbon gas, which is the function of the gas gravity. And this gas gravity here, this is the total gas gravity containing the non-hydrocarbon component, meaning what is measured in the lab. And then you need to know the amounts of different non-hydrocarbon components, so like nitrogen, H2S, CO2. And yeah, so again, like this equation, how do you calculate this using these numbers here? This is given in the SPE monograph, the equations, and we will see those equations being implemented in the Excel sheet that we'll be using for this QC. The second QC, the second step here, is that you calculate the TPC and PPC of the hydrocarbon, which will be a function of the hydrocarbon gas composition, the hydrocarbon gas gravity. And again, this we know, like there are a bunch of correlations. So like for example, you can use this Sutton correlation. And then the third and the last step is that when you have this, for example, TPC, the corrected, like when you have this TPC of the hydrocarbon, you can calculate this TPC star, which is the TPC of the entire mixture, as a function of TPC hydrocarbon, and need to know the TCI and the amount of the non-hydrocarbon components. So this is valid for non-hydrocarbon components. You need the TPC, the entire mixture TPC of the hydrocarbon mixture, and the individual component TC, and the amounts of the non-hydrocarbon components. So these three steps are needed. Once you have this, now once you have the TPC star, you can calculate the corrected TPC and PPC using these equation here, and then you can calculate the corrected TPC and PPC using these equations here, and then you can calculate the gas Z factor. And these three equations here for this these are given in the monograph, and also we will look at them in the Excel spreadsheet. So this was all on the theoretical side of how are we going to implement the QC, and now we will look at the this Excel spreadsheet that we will use for this QC. And so yeah, so first we go Z factor QC Excel spreadsheet. Okay. Yeah, so this will be the Excel spreadsheet that we will be using, and there are a bunch of spreadsheets. So the relevant spreadsheet for us for entering the data is this spreadsheet here. So what we'll be entering here is that pressure versus the lab reported Z factors and the associated gas compositions here. Okay, so for this we have the PVT report on the CVD on the gas condensate. So this is our gas condensate PVT report, and then we have CCE experiment where we have the reported gas Z factors as a function of pressure, and then we have also CVD gas Z factors as a function of pressure. So so first what we will do is we will copy the pressures uh, here in this column, and then go to the CVD again, copy all the pressures. Yeah, so yeah, so we didn't copy the first one because the dew point, and it's we copied it from the CCE experiment. So now I'm going to copy the gas Z factors until the dew point from the CCE experiment, and then we are going to copy the gas like the Z factors from the CVD experiment, and this first one and the dew point has to be the same as in the CCE experiment. Okay, and then we just keep the same values at all rows below because like if you have more rows, then you can still use this spreadsheet. So this is just to make the spreadsheet usable if you have more stages in either CCE or CVD. Now the next step is to enter the compositions, and so now when we are entering the composition, we should be aware that when you do a CCE experiment, the composition is constant, and like the total composition in the PVT cell is constant, and for the Z factors reported above the dew point pressure here, the composition has to be the same composition as reported for the entire mixture here in the PVT report. So whatever the total composition here is, that's the total composition of the fluid that they use in the PVT cell for measuring the composition. That composition should remain the same for Z factor calculations for all pressures higher than the dew point. And in the CVD, the total composition, the gas composition is changing at each pressure, which is reported by the PVT lab here. And this is this composition here at the dew point. It should be the same composition that is that's given here actually, or it should be very similar. Yeah. Okay, so what we will do here is that we copy these composition, copy it from C1 to C7 plus first, So, and we paste it from the dew point, which is this 6726 psi, and then we have to transpose it so that the components match here. Something went wrong. We go back. Oh, something went wrong in this report here. Just need to close the spreadsheet and open the report again. Hmm. It seems like there has been some error in this report because I can see that these compositions have been changed. So what I can do, yeah, I can just replace this PVT report here with the correct file actually. So if I go, okay, let's open this again. Okay, so we can do it again. So copy the composition and place it here. Exposing it, and then for the non-hydrocarbons, we again copy and paste here, and then H2S has to be 0, and then we just keep the same composition until 8000 psi because we know that it has to be the same for all pressures higher than the saturation pressure. Now the other information we have is the C7 plus molecular weight, which we again copy. And one comment about this composition here, because you see that there are two compositions reported 500 and there is a star here. So this is actually the it's not the gas composition, it's the oil equilibrium oil composition at 500 psi, which is the residual oil. And we will not use this composition in the gas Z factor QC because it's not needed there, but this composition plays very important role in doing the QC of the CVD test itself. So yeah, so that is something we will discuss later, but that's something we don't need now. And so we have at least all the data here in the Excel spreadsheet, and also that's very important to enter the temperature, the correct temperature used for the PVT experiment, which is 250 °F. So that's something we have entered here. The C7 plus molecular weight, we just keep it the same for all pressures higher than saturation pressure. Oh yeah, there is one thing that we also need to input, that's the specific gravity, the lab specific gravity of the gas mixture. So we go to the report and we find it here. See that it's gas gravity reported for the different gases in the CVD. So we just copy it here from the dew point. And yeah, it should be the same for all pressures higher than saturation pressure. So again, it's the same. And then so we have the C7 plus molecular weight in the lab, but we don't have the C7 plus specific gravity. So there, one alternative there is that we can use some kind of correlation to come up with an estimate of the C7 plus specific gravity. And one correlation that we can use is this Soreda correlation that relates the gravity and the molecular weight. So this is Soreda correlation, uh, and we know that this C7 plus molecular weight and gravity, these numbers, they are used for calculating the TC and PC of the C7 plus fraction only using this Matthews correlation, and which is used in this in the calculation of the TPC and PPC from case mixing rule. The Sutton correlation, it is gonna use only the lab specific gravity, so it's gonna only use this number here. It's not this not uh, dependent on the C7 plus molecular weight and specific gravity. So that's why we have two methods. If you one is just using the lab reported specific gravity, uh, which is Sutton correlation, and the other one is using this case mixing rule where should know the entire composition and the molecular weight and specific gravity of the C7 plus fraction. So for now, we just use this correlation 0.2855 plus 0.29 times the molecular weight minus 66 times 0.13. So that's the specific gravity number that we got for C7 plus, and then we just drag it down to get other numbers. And then, so this is all the data that we need. So again, if you the lab if you have the C7 plus specific gravity reported in the PVT report, then you should use those numbers instead of using some kind of correlation. So that's an important point to note here. And so if you scroll down in this sheet, what you find out that here uh, there's here the different calculations are being made, and these are calculations are the same that I tried to point out in the PowerPoint, actually calculating that C7 plus TCPC, for example, from this Matthews correlation, and calculating the hydrocarbon gas gravity, calculating TPC and PPC for hydrocarbon gas, this epsilon correction, and then calculating the correct TPC and PPC uh, from Sutton correlation and the case mixing rule, or the Sutton correlation and the case mixing rule. And then so all these calculations are already programmed here. You can, if you want to know, if you want to understand how these equations are being implemented, you can just double check them with the equations given in the SPA monograph. And on this sheet here, this first sheet here, they actually using this information from this average gas properties, which is TPC and PPC, the gas Z factors are actually calculated. So you have a set of gas Z factors calculated from certain correlation and a gas Z factor calculated using the case mixing rules TPC and PPC. And then these are the lab reported gas Z factors, um, which are linked to this sheet here where we entered the data. So once you have entered the data, we can look at the plot, how it looks. So how the data corresponds to how the data looks corresponding to the different correlations here, different methods of calculating the Z factors. So you see that we have the data in the red points. We have error bars of plus minus 3% here. And then what you see, that blue line, which is the certain correlation, giving the gas Z factors, or like giving the TPC and PPC for calculating the gas Z factors. It falls almost spot on the gas Z factor values. And this composition based TPC PPC, which is actually this case mixing rule, it's falling below this certain correlation. But yeah, the one reason why this composition based TPC and PPC, or like this case mixing rule TPC and PPC, is not giving accurate representation of the lab data is that had we made this assumption of this correlation, like Soreda correlation, to calculate the C7 plus specific gravity, which may not be a very good correlation for that purpose. But what we see from here that the acceptance correlation is giving you very good representation of the lab data. And that's something we recommend, that you should try to use both methods for doing the QC of the lab reported Z factor. And if either of the two methods or both methods give you very accurate representation of the lab reported gas Z factors, it means the gas Z factors are of good quality and they should be used, or they should be matched with an equation of state model if you are using it in tuning the US model. Okay, so yeah, so I think here we finished this gas Z factor topic, and then we will jump to the next topic, which is the QC of the separator K values, or like checking whether the separator samples are in equilibrium or not.